Now we are going to model a DC motor. When we model a DC motor, we should understand the nature of a DC motor itself, where the torque is directly proportional to phi, that is the field, and armature current. Okay, so this is the block diagram of the DC motor which we are discussing about, and this DC motor is a PMDC DC motor. Okay, so what is PMDC DC motor? This is a permanent magnet DC motor. Permanent magnet DC motor means the field are excited by a permanent magnet. So when we say permanent magnet is exciting the field, which also means that the field remains constant. So this term, phi terms also becomes constant. So the torque is directly proportional to Ia now. So if I write this as an equation, the torque is equal to, let's say I have a constant Kt which is multiplied with Ia, which is the armature current. Okay. If we calculate the back EMF, this is the torque equation. If we calculate the back EMF is again directly proportional to speed. Okay, here we have mentioned speed as EB speed is theta A dot, and we can also rewrite this equation with a constant which is EB is equal to KB theta A dot. KB is a back EMF constant. Okay, if you write the equation of a DC motor itself, this becomes EA, because if you see this here, EA is the voltage. So EA is equal to IARA plus EB. Here in this case, which is IARA plus EB. Okay, we know what is EB. So IARA plus KB times theta A dot. Okay, so what happens here is the sensor detects the position as well as speed of the joint. Okay, or I can say the angular position and angular velocity of the joint here, and give this as a feedback. And this joint control system decides the torque to be provided, the desired torque to be provided, and this motor driver circuitry provides the voltage to the DC motor here. Okay, so this DC motor provides sufficient torque to the joint based on this desired torque as well as the voltage, which is again continuously tuned by these feedbacks. Okay, so this is how a DC motor works. This is a model of a DC motor.